Hello ladies and gentlemen, and welcome to the smallest possible domain screencast for today. We spent a couple of days looking at restricting the domain, and today, and maybe tomorrow, we'll be looking at the smallest possible domain for a particular function. So let's do a little review. Let's graph some inequalities on a number line. Now if you recall, when you're graphing on a number line, either you have an open circle or a closed circle. The closed circle would be, for a graph like this first one, x is greater than or equal to -3. Whenever you have equality expressed, either greater than or equal to or less than or equal to, you need a solid dot. If it's just greater than or less than, it's an open circle. So this will be an open circle, the graph of this, at -3, and since x is greater than, we're shading to the right. We're drawing an arrow to the right. So let's take a look at another one. On this one, x is less than 2 and greater than 6. So the graph of this would be open circles. I put these little bullseye things from the Smartboard files there instead of an open circle. So they will, from now on, we're going to use these bullseyes as open circles, and a dot like I have up here on the -3 is a closed circle. So where x is less than 2, so maybe I should show the number line, that might help. I have the open circle at 2, less than is shaded to the left. Then I have an open circle at 6, greater than is shaded to the right. So let's look at another one. Let's look at how we can find the smallest possible domain for a function. So if we look at this function, f of x is the square root of 3x plus 9 over the square root of x minus 1. So let's do a little review of what we looked at a couple of days ago with the restricted domain. If you have a radical in the numerator, you're going to take what's under the radical sign and set it to greater than or equal to 0. Because we can't have a numerator of 0, so that's fine. So you set that 3x plus 9 greater than or equal to 0. You solve it for x. X is greater than or equal to -3. Now the denominator cannot be equal to 0. So when you have a radical in the denominator, like we have, square root of x minus 1, you set that to greater than 0. Not greater than or equal to. It's greater than 0. So then we have x is greater than 1. So in this first instance, x is greater than or equal to -3. That will be a solid dot at -3. And x is greater than 1 would be an open circle at +1. So if we look at this, here's my solid dot at -3, arrow to the right. Here's my open circle at +1, arrow to the right. Well, the smallest possible domain is we're looking for all values that will make the function work. So the values between -3 and +1, they won't work in this function because it will cause either the numerator or denominator to not be compliant with what we're looking for. So that's why I drew this black line here. So that black line and everything to the right of it, if you see the two red arrows are running together, that's the smallest possible domain. So since we have the open circle at 1, I have parentheses 1, comma, infinity. Because every value greater than 1 works for both the numerator and denominator of this function. So that's what the smallest possible domain is. We're looking for values that will work numerator and denominator, not just one or the other. So let's look at another example. F of x is equal to the square root of x minus 2 over simply x minus 3. Okay. So if we take a look at how to set this up, x minus 2 is greater than or equal to 0 because it is a numerator even though it's a radical. So when we solve that, we find out that x is greater than 2. For the denominator, what we are looking for is all values of x that will cause us to have a 0. So we want to find out x minus 3 is not equal to 0. And we solve that, we find out that x cannot be equal to 3. So every value except 3 is a valid value for our numerator, for our denominator. So when I graphed the x is not equal to 3, that's the open circle, that bullseye, and every value to the right of 3 and every value to the left of 3 work. However, when we look at the numerator, only values of 2 and greater than 2 work. So again, I drew some lines. So I have the line here at positive 2, and I drew just to the left of 3. And so these areas where the two red lines coincide, they're solutions, or they're possible values for our domain. 3 is not a possible value for the domain at all because it will not work for our denominator. But everything to the right of 3, where you see the two red lines running together again, they're valid values for our domain. So when I put this in interval notation, the smallest possible domain is everything starting at 2, ending just before 3. Then we're going to hop over 3, and everything from 3 to the right of 3 will work in both numerator and denominator. So when I put these in interval notation, you'll notice I put a union sign because it's all these values from 2, including 2, to just before 3, and everything to the right of 3. They're all possible values for the domain. So now you guys try one. Pause the video if you need to try and work on this problem. So if you look at this, you have a numerator of the square root of x plus 5 that you would set to x plus 5 is greater than or equal to 0, and your denominator is the square root of x squared minus 16, which must be greater than 0. So if you look at the way I set these up, I have x plus 5 is greater than or equal to 0, so x is greater than or equal to negative 5, then x squared minus 16 is greater than 0. There is a typo here. This should be x is less than negative 4. Let me see if I can put this in with my tablet. I guess the tablet's not working. So I will correct that. But just remember, there should be a negative 4 right here. X is less than negative 4. And then x is greater than 4. At least I graphed it right. So it's graphed correctly. If you look at this, I have an open circle at negative 4, and it's less than negative 4, so it's everything shaded to the left. X is greater than 4, open circle there, everything shaded to the right. Then for the numerator, I have x is greater than or equal to negative 5, that's the red circle, everything to the right is shaded. So to look at the smallest possible domain, you need to see where the two lines are running concurrently. So the two red lines here are running concurrently from negative 5 to just before negative 4, and they run concurrently just after 4 to positive infinity. So if I were to put those in interval notation, this is how the smallest possible domain would be represented. Starting at negative 5, including negative 5 to just before negative 4, union, everything after 4 to positive infinity. So bring any questions you may have to class tomorrow, and we'll be doing practice problems on smallest possible domain. So thank you for viewing the screencast tonight, and this is the end of the smallest possible domain screencast.